All right. Hopefully by now we've done chapter 9. So now we're on chapter 10, and this is strain. Linear strain. So, I think I've been alluding to it this whole time, but when you pull on something, what happens? It deforms, it stretches out. That's a pretty extreme example, is a big ass spring like that. So strain, this little E symbol, E is equal to this squiggly D over L. And D is the change in length. L is the original length. So if you measure this, say it's 7 inches, and then you stretch it to 12, which is pretty extraordinary. Then you get strain upwards of like higher than 0.5, which would be like 50% elongation. I'll just roughen the numbers, I'm sorry. It's conceptual. So that's what they're talking about here. So strain is a ratio of two lengths. It's dimensionless, which is pretty bizarre. But since it's like it's a ratio now, but we're gonna write inch per inch just to keep track. And there's not too many things like that. And you might be familiar with this, Hooke's law. It probably showed up in physics, and it branches off into extreme detail in mechanical engineering and civil engineering. And this form right here. So Hooke's law force is equal to some constant times your delta x, really. So everything has a slightly different spring constant. So like this spring was really easy to stretch. Like I could do it with my hands. So I'm going to say its spring constant is really low. Meanwhile, this chopstick is slightly higher, and you probably can't see any deformation as hard as I can pull. And so its spring constant is really high. So strain is very general. Yeah, so in the same vein, stress is equal to some constant E times a unitless strain. So sigma stress, E is some constant. And I will use this interchangeably. Or elastic modulus and strain. And so this is just Hooke's law, but in a form that is useful in general. Yeah. Also, yes, E is like in steel, it's going to be a very, very big number. And so I think we've been seeing stresses in megapascal up until this point. The modulus is in gigapascal. So for a couple hundred megapascal, you're only going to get minute changes in length. For steel anyway. Unless it's a spring. Intentional design. And yeah, that's kind of what it says here. Steel 70 gigapascal or 10,000 KSI. And that's for aluminum. And steel is 3 times stiffer, 30,000 KSI. Yeah, 30,000 sounds pretty right. Cool. So down here, stress from our definition is force over area. And now we just introduced that strain is the change in length over the original length. So you can substitute those into that simple Hooke's law equation. And so you'll end up with F over A is equal to elastic modulus times the change in length over the original length. And in that form, it's no longer unitless and very specific to what you're working with. So you could do pretty powerful things with these, like predict deflection or elongation. Yeah, right here. So they solve for D. Divide both sides by E, multiply both sides by L. So LF E A is equal to change in length. And, you know, through the problems, they will probably just throw any of these forms that they feel like in, and you need just to remember that it's only Hooke's law. Cool. Yeah, the equation they just came up with where strain is change in length over length is specifically for axial force. And what I mean by that is if I had force that was like shear, for example, now that's not change in length over length. That's something, that's a different, but this is axial. Spring's fun. All right, so example 10.1. A 2 meter long steel tie rod and